unfortunately, one of our speakers couldn't come in person, but we're able to have her kind of zoom in. So this will be a Zoom talk, and we'll hopefully have this work okay. So we're very happy to have Muyang in Uppsala. Please go ahead.
Sure. Okay, good morning, everyone. So let me first thank the organizer to give me the opportunity to present my recent work on the study of the properties in the Heterotic ALE Instantonic Lagrangian series. So I hope it's a pity that I cannot be there in person since my graduation in Penn, but I hope I can be there in person visiting in the future. So, one second. Okay. So this talk will be based on biology of the recent published as well as one upcoming published work. So in which that in part one, we focus on the theoretic perspective argument of the properties of ALE instantonics, heterotic string series, and on the part two, we focus on the geometric engineering. In the upcoming work, as well as mentioned in Michaela's lecture talk, we explore the geometric engineering limit to study heterotic string series. And there's also another work in progress with the mathematician Andreas Bruns, as well as the group member in the triology work, Michaela Dalzotto and Paul Ullman. So we anticipate to use the knowledge of the K3 geometries to produce more fruitful novel Lagrangian series families. So far, we know that the Lagrangian series to describe the world volumes of the heterotic spin 32-mile Z2 ALE instantons. They are known because they are Lagrangian, can be obtained by the OB foldings of the stack of the NS fibrations. However, most Lagrangian series of the Heterotic E8 cross E8 instantons are non-unknown. With the exception studied by Aspinwall and Morrison, they keep the Flavor groups to be unbroken. And there's also some other work that focus on the small breakings. So nevertheless, the Lagrangian series in associated to heterotic E8 cross E8 instance are incomplete. So that motivates us to combine the recent understandings of the 60 series as well as the higher group structure and higher form structure the symmetry studies on those series to find and determine novel Lagrangian series by the 60 conformal method. And we also use the two group structures to as a matching criteria to find the T2 partners of the novel Lagrangian series we found in part one. And in particular, the old Lagrangian series has universal one-form U1 symmetries, which forms two group structures. As I mentioned earlier, they provide very restricted constraining to verify the T-dualities. And this is the outline of my talk. From the field theoretical perspective, which is the first two sections, that we employ the 60 conformal method to explore the novel heterotic E8 cross E8 ALE instantons, and we confirm that they are T-dual to at least one known spin 32-mile Z2 ALE instantons Lagrangian series. From the geometric constructions, we realize 61,0 Lagrangian series, where the geometric engineering in F series, such that the T-dualities are realized as the inequivalent elliptic fibration structures of the same geometries. In particular, we employ the toric method to construct elliptic fiber Calabi-Yau threefold to produce novel Lagrangian series, and also in a non-geometric background, we can build a Lagrangian series from the extremal K3 surface where the toric realization is lacking. So here is a quick review of the results. I put one of the most attractive novel Lagrangian series families we found in the non-geometric background. So that I will tell you details about how we render such exotic Lagrangian series families at the end of the talk. And here I used the black font to indicate the types of the flavor groups. And I used the brown color to indicate the types of singularity they are probing to. So they all passed the T-duality, or sorry, T-multi-dualities conditions I proposed with the two group structures. And I also prefer to make this talk on Monday about the geometric engineering of heterotic strings in ALE spaces. So in this section, I will quickly review the basic properties of the little string series in 6D, as well as some convention and notation we are going to use to describe the generalized quiver. So what is a string theory? In 6D, they are like the cousins between more familiar local and gravitational series, such that they are set the compactification chains from the supergravity to little string theory to SFTs. That allows the little string theory to capture some features of the supergravity and the SFTs. So namely, if we compare to supergravity, the string theory also has a scale called the little string theory scales. That is the key in the dynamics of the series. And we can also talk about the T-dualities arising from the circle reductions of the 6D compactifications. So similar to SCFT, this string theory is decoupled from the gravity, and we can talk about many interesting global symmetries, which will enter the two group structures in the talk. So here is a quick review of the convention I will use to describe the most generic 6D quiver. So the quiver I denoted in brown will be encoded by two sets of data. One is composed by the matrix that is recorded informations of the compact components as well as the intersections with the non-compact components in the base of the string series. And this is tuples of the algebra to denote the gauge algebra as well as the flavor group algebras in the quiver. So in particular, if eta ij is very important because it must be non-negative for the string series, and it contains unique no eigenvectors, where the eigenvector will associate to a string charge Ni that features the background, the two-form tensor field. And these two tensor fields will relate to a universal one-form symmetries of the strings. And from the green flash terms, you can see that there's a mixing of the zero-form global symmetries with these universal one-form symmetries, such that the two T-dual little string series must have the matching following data. The first category is compromised by 3 structural constants, which controls the mixing of the symmetries. So you can see that the string charges enter the computations of the structural constants. And then they must also have the matching Coulomb branch dimensions. So in particular, the structural constant associated with R symmetries as well as the Coulomb dimension, they are very constraining. And in the most topic quiver we talk in these presentations, Kp remains to be a fixed number too. So we anticipate to investigate more general string theory quivers for the various choices of Kp in the future. And then in this section, I will talk about how we introduce the heterotic instantons on various ALE spaces. So in the M-theory pictures, that we can realize the exceptional string series arising from a stack of the M5 rings in parallel to the two M9 rings, where the presence of the ALE singularities makes the instantonic configuration to be fractional, and the resulting instantons will depend on choices of the flat connections encoded in the following mapping. So for the choices to be trivial, then the cases that are being studied well by the Aspinwall and Morrison. And right now we focus on considering all other possible choices, where the fractional instantons can be determined by the F-theory method. So this will render the generic 6D string theory quiver composed by the 3 components. So actually, there are 3 components that can be described by the SFTs. So the first part is nothing but the 6D OB instanton series associated to a single M9 and fibrines. And in the middle, you have the 60 conformal matter series associated to the N-2 fibrines. And then you just fuse the common factors of the global symmetries of the 3 SFT components to cook the Lagrangian series equivalent. And given the matching criteria associated with two group structures to the Coulomb branch dimensions, we are able to check the T-duality between the novel Lagrangian series we found by fusing the components, as well as the known heterotic spin 32 Z2 instantons. So for instance, let's talk about the examples relevant to the heterotic instantons on exceptional singularities. So this can be expressed in the generic form where you can take S, R, Q to be any numbers between 6 and 7 and 8. So we present all possibilities in our work. And we found at least one heterotic spin 32 Z2 instantonic Lagrangian series will satisfy the T-duality conditions. So for instance, if we take Q equals to 6, we are proving copies of the E6 gauges in the middle. The corresponding T-dual series is described by the chain below, where the Vi and the Wi still are functions of the N, and they are determined by the right connection choices in the lambda in the spin 32 Z2 instanton series. And in the second half of my talk, I will give more details about the geometric engineering of heterotic E8 instantons. So first of all, this is to show how you generalize geometric engineering the Lagrangian series from the F series. So namely, we use the elliptic fiber, the Calabi-Yau threefold, to describe the 60 Lagrangian series. And of course, this threefold can admit multiple inequivalent fibration structures. And the base of the fibration structures is non-compact that reflects the fact that the Lagrangian series is decoupled from gravity. And the threefold will become singular over the discriminant locus of the base, such that they will contain compact and non-compact components to allow the D7 branes to wrap, while the former one will produce the gauge degrees of the burden, and the later one will produce the free symmetries. So in the perspective for the F-series geometric engineerings, we can obtain the same 5D series after circle reductions, and they will have multiple inequivalent 60 uplifts in the F-series. That's how we talk about the geometric realizations of T-duality between two or even multiple 60 series. And then we just engineering heterotic instantons by emergence of the C2 of the C2 mod Zn singularities. So this is a visualizations of the putting such instantons in the underlying case-series of our Calabi-Yau threefold in the degenerations limit of the case-series. So I will talk more details about the case-series fibrations in the later slides. So due to the incorporations of the Kodara fiber G in the middle, that the bottoms reference to the singular threefold, which you need resolutions by blow up in the middle that gives you the full 60 quivers. And since we heavily used toric constructions to build our non-compact Calabi-Yau threefold, I will quickly review the toric basic knowledge that will give you the idea about how we obtain the Calabi-Yau threefold. So we use concrete 60 polytope delta to obtain the toric ambient space. And then our Calabi-Yau threefold is nothing but the anti-canonical hypersurface in this toric ambient space. So this structure is very nice because the elliptic fibration structure on X is also inherited from the fibration structures in the ambient space. So there's a group of Virginia Tech people that talks about the thesis and also about the group of the Wati, and Huang talks about the anti-canonical hypersurface in toric cases. And given these vibration structures, our B2 just coincidence with the literature series basis B2 P1 times C. And these fibers in the toric ambient space, they will generate anti-canonic hypersurface, which is just the torus that fibers of our literature series basis. So in practice, we noticed that the Calabi-Yau threefold also admit the structures of the K3 fibrations over the C, such that we can use as reflexive 3D polytopes to build the fibration over C to build our toric ambient space. So this 3D polytope will tell us information of the K3 fibers that determines the flavor groups of the series. So let's talk about one example, which is also very famous. That's namely, we embed the generic literature series base B2 into the toric fourfold, such that we decorate additional base series into the literature series base B2, that each race associated to the yielding additional n copies of the E8 instantons. So those additional rays are very trivial because they don't support any non-trivial gauge algebras. And in the T-duality vibration structures, it is reflected that the T-dual series will have a non-trivial gauge groups. So then, of course, we utilize the formulas of the two group structure constant as well as the Coulomb dimension mentions that it's obvious that those two T series pass the T-duality conditions. And of course, now we can decorate more non-trivial gauge algebras on each additional race, and that will give you more rich structures in the T-dual series. So let's see one more example here. Here we gauging the E8 cross E7 flavor factors by probing M copies of E7, E6, and we obtain the following quiver. And you can include conformal matter factors that to inside of each say E8, E6, and E6, E6, and E6, E7 to give you the full Gen 60 string theory quiver. And using the torus fibration, we find another TDR series described as the second torus fibration, which has F13 fiber types with Z2 module torsion groups. So the dual chain is described as following. And they have matching two group data and Coulomb branch dimensions. And in this section, I want to talk about more exotic literature series family we found. So it is compromised by two parts. The first part, I will talk about the incorporations of more non-trivial global structures, means that it is associated to the discrete holonomy series. And in the second, I will talk about the K3s in the underlies Calabi-Yau threefold, such that its fibrations as well as degenerations will give you multiple novel literature series families. And first, we want to investigate more general geometric models with a non-trivial global structure, namely that the fibration admits non-trivial section structures such that the torsion groups will impact the total groups, namely that the overall group of the flavor and the gauge group will be quotient by these torsion groups. That will break the E8 flavor factors via the discrete holonomy ZNs. In our current work, we focus on the rank preserving case. So this torsion part is also have a beautiful toric realizations because it is reflected by the different fiber types Fi respectively. So let's say one example. So this is the T2 discrete holonomy literature series, which has two possible breakings. And we consider breakings to E7 cross SU2, and they are probing M copies of E7 gauges, such as the generalized quiver. And its toric realization actually has two more inequivalent toric fibrations. So the first one is given by the following chains, and it is a very interesting property because the dual chains has the full E7 topology. So it is a nicely demonstration about the fiber-based duality, namely the dual series will have the base topology that reflects the types of the gaugings you are probing to the original series. And the third fibration has more interesting factor because the base topology is no longer E7. That's because in the third fibration descriptions, the chain has the topologies of the twisted affine phototypes. Namely, there are some additional base rays that identified if you describe in the third fibration structures. So at the end, it has the E6 to the 2 base topology. And of course, those 3 within theory quivers, they match the T-duality conditions as I listed here. And in the later part of the talk, I want to use the knowledge we obtained from the underlying K3s in the Calabi-Yau threefold to produce more novel little series families. So just to recall a little bit that thanks to the F-series heterotic dualities that in 8D, we can study the heterotic strings obtained from the stable degeneration limit. But from the other perspective, you can also see that the E8 cross E8 bundles can be embedded into the Picard sublattice choices in the second homology groups of the K3s, where the lambda K3 is just the intersection forms associated to the homology lattice. And if you keep the E8 cross E8 to be unbroken, that is just this very trivial decompositions of the lambda K3s. But in general, we can consider about more types of the decompositions. Then namely lambda K3 is split into two parts. The NS lattice parts that will record the informations of divisor intersection forms, and they are spanned by divisors modular rational equivalence. And the transcendental part will record the complex structural deformations. So namely, if you're tilting the transcendental part, they will render to different decompositions or also render to the different types of the Fourier groups. And then we can translate the findings of the inequivalent elliptic fibrations in the lattice language. Namely, we just find the distinct embeddings of the hyperbolic lattice U into the NS lattice, such that there is a so-called frame lattice encoded in the NS lattice will tell you the types of the AD root lattice associated to the types of the Fourier algebra. And also, you can read the multiple groups from the frame lattice. Then we moved to the 60. This is just fibering the elliptic K3s or non-compact directions, such that the overall Calabi-Yau threefold has the nested fibration structures. And now, to introduce more interesting non-trivial dynamics to the Calabi-Yau threefold, we just add non-trivial compact curve to the base of the Calabi-Yau threefold. That will render the K3 to be degenerated at that point you introduce non-trivial compact curves, such that the Lagrangian theory is localized at origins of the C. And after resolutions, it will give you the generalized 60 quivers of the resulting Lagrangian series. Then we can just feature the properties of the 60 Lagrangian series by the inequivalent elliptic fibrations of the K3 as well as its degenerations once you move the 260. And in 60s, the lambda K3 that encoded the homology lattice of the K3 will connect to the intersection forms of the non-compact divisors, DIs inside the Calabi-Yau threefold once they restricted to the K3 surface. So that's how the K3 that is connects to the Calabi-Yau threefold in the lattice perspective. And in particular, in our work, we focus on an extremal K3 surface in the current work, namely the Picard rank is maximum, rank 20, and the total flavor group rank will be 18. We expected to identify distinct T-dual string theory to associate to inequivalent elliptic fibrations of the same K3s. So let me just elaborate a little bit more about the K3 degenerations because it features and it also opens a new direction to investigate the 6-digit string theory properties. So in the math literature by the Coulomb, some specific degenerate K3 can be described in 3 types of the Coulomb models. Well, Coulomb models is just once described by a smooth K3 fibered over C, but once you move to the origins of the C, the fiber becomes singular, and this singular part will generate out many more interesting parts of the dynamics in the 60 series. And here, but unfortunately, in most cases of the string theory we study in our work, they don't fit into the 3 previous types of the Coulomb model studied by the literature. Namely, we hope to investigate a Coulomb-like ways of the models to study the K3 degenerations. So these depictions is a nice visualization of the K3 degeneration, namely that away from the origins, it is just the 2 rational equivalent surface that talks to intersect with each other. But once you move to the origins, there are more compact surface will be emerged that tells you the details of the 6-digit string theory quivers. And then I gave one interesting examples about the multi-T-dual families that used the knowledge of the K3 geometries. Namely that there are 6 different flavor groups that are depicted in each corners of the hexagon that reflects to the different elliptic fibration of the same K3s. And then we conjecture that any consistent string theory configuration with a fixed flavor group, here I'm talking about the E8 square times SU3, probing the F4 singularities, they must admit the rest dual series from each other flavor groups in the same K3s. So we test the probings of F4 in the 1 corners of the T-hexality families, and we use the Coulomb structural constant as well as the Coulomb dimensions as a criteria, also as a constraint about all the possible singularity types can be proved by the rest 5 corners of the T-hexality families, such that at the end we obtained a nicely exotic Lagrangian family compromised by the 6 types of them. So here I want to give a quick summary of the work done by our recent project. We construct many normal string theories probing various types, namely all types of the singularity A, B, C, D, E, F, Gs. And we confirm the T-dualities verified by the Coulomb and tensor branch data emissions. And in particular, we use the F-series geometrics to engineering the heterotic series in non-compact Calabi-Yau threefold. And moreover, at the end of our work, we can also find more interesting exotic string theory in the non-geometric background. And in the future, we anticipate to turn towards to non-heterotic string theory given by the systems without neighborings. This is not associated to the base that we talked before, namely P1 magnitude. It is associated to the other types of the string theory bases that can be realized by thesis. And we can also incorporate the possibility of the twisted compactifications that usually resist to the genus 1 fibrations rather than the elliptic fibrations. And given by the knowledge of the K3 geometries, we hope to relate more heterotic string theories to the classifications of the degenerate K3 surface. And we hope to study more Kulikov-like models that refers to the reducible components in the K3 degenerations that occurs in most parts of the our string theory that we studied so far. So I think that's all. Thank you.
Okay, thank you, Muyang. Okay, maybe I'll ask a question. So you, the main idea was to use basically different choices of elliptic fibrations to find different dualities or hexalities in some case. Do you have an idea of like what the maximal number of analities would be?
So I know there's interesting work done in thesis to get the unbounded types of fibrations. But in our perspective so far, we haven't studied the possibilities of the infinite vibrations. So it might be from the K3 lattice perspective, because the limitations of the complex structural deformation you can have by the transcendental lattice, it's very hard to believe that it can have unlimited possible choices of the vibrations. So far it's still open questions.